Assalamu alaikum. Welcome to the second class of the electrical machines first. So in this class we'll start from the Ampere circuit law. As I've told you, these are the important uh, there are some important topics which we need to cover before starting the actual topic. So the relationship between B and H is given by V is equal to mu into H, where V is the magnetic flux density, that is Weber per meter square, its unit, or sometimes its unit may be used as Tesla. H is the magnetic field intensity, its unit is ampere turn per meter, where mu is equal to mu naught into mu r, where mu r is the relative permeability, and mu naught is the permeability of the vacuum or absolute permeability, its unit is Henry per meter. So from the basic studies, you might have studied that this closed line integral of B dot dl will be equal to mu into I encircled, where I encircled is the current that is encircled by this closed surface. So replacing B, or we can say dividing dividing this whole equation by mu, we'll get B divided by mu dot dl is equal to I encircled. So B divided by mu from this equation will be equal to H dot dl. So this is the actual equation that you might have studied in the electromagnetic field theory. So this is the integral form of the Ampere circuit law. So here we need to first find out the value of this I encircled for a particular case. Now let us first start a simple magnetic system where we have this core which is made of ferromagnetic material or simply magnetic material, and we have an exciting coil which is made of N turns. So let us say we have a DC current or DC voltage that is applied to it, so which forces current to flow in it. So this will be the pattern of the flux in the core. As we know that for an electric circuit, resistance try to oppose the flow of current, and current will try to flow through the least resistance path. So by using the same analogy, you will see that there is a term known as reluctance which opposes the flow of flux, uh, or we can say which oppose the passage of flux. So the reluctance of the iron, or we can say magnetic material, is less as compared to the reluctance of the air. So in that case, the flux will try to mostly flow through the this iron path or magnetic material path. So in that case, we have the most of the flux will flow through this path, as I have shown you, and some flux may be flowing through this air because here we have air. So the flux that flows through the air, which is not a desired one, and it is not flowing through this core, it is known as leakage flux. So I have shown you over here both the fluxes. One is this, the actual, that is known as the mutual flux, or we can say the actual flux, and this is the leakage flux. Leakage flux is usually not important to us. It is actually leaked to the air, and which does not do our proper work, that is desired work. One more thing that is important over here, there will be a flux line which may be very close to this, whose length will be simply equal to, flux line length will be equal to the length of this square. And we might have a flux line that may be flowing through this, like this, and then this and this, whose length will be equal to the, you can say, perimeter of this square. But in this case, you will see that the length of this square will be greater than the length of this square. So usually we take the mean value of these length. So that is, so we consider length of the flux line to be this one, which is at the middle of this, and it is known as core mean length, or flux line, mean flux line, this one, because its length will be definitely the mean between this and this, it is at the middle of this. So we always take the flux line length to be the flux line which is flowing at the middle of this core. And for practical purposes, we always neglect this leakage flux, and we always say that all the flux is flowing through the iron path. There is no flux that's leaked through this air. So that means all the flux is of use for us. There is no flux which is not linking to this core. So now actually I have to find out this I encircle how much current is encircled by this closed surface. It depends upon the uh, surface that you choose, and due to that surface you will be able to find out this I encircled. So for this case I'm using the same exciting system or magnetic system, and I'm having a cross section of this in between this. That means I'm cutting it upside down, so it will look like this. At every turn, at one turn, you can see from here to here the current is entering at this point, and the entering means a dot, and at this point current is leaving, and we can see that the leaving means uh, sorry, the current is entering is at this point, entering means it is cross, and the current is leaving at this point, it means it is dot. So its cross section I have shown like this. So since I am assuming that for practical purpose there is no leakage flux, all the flux will be through this inside, will be inside this coil or inside this solenoid. So when we use this type of the Gaussian surface, you will see that in this direction. So you will see that this B dot ds, B dot dl, this B or H dot dl, you can see this and this line and this line, they are perpendicular to this magnetic flux lines. So in that case B dot dl will be 0. For this case, since there is no B, we are assuming there will be no leakage flux, only flux will be over here. So from here to here we are assuming that the total number of turns are n, and total current will be equal to n. Sorry, total current will be through every conductor, it will be I. So the total current that is encircled by this Gaussian surface will be equal to n into I. So in that case, one more thing, the total current that has been calculated will be equal to n into I, because we are actually taking the Gaussian surface to be like this from here to here to here. The total current will be Ni. We are actually here we haven't enclosed all the current, but here we are enclosing all the current, all the coil in the Gaussian surface. So total current will be equal to N into I. One more thing, you can see we have this length element, that is dl. It is in the same direction of the B. So H dot dl or B dot dl will be equal to B into L. And from this to this, you will see that there will be a constant value of the B or H from here to here inside this solenoid. So we can take this H outside. H outside, it will be equal to dl. So dl, from here we can say that this dl will be nothing but this LC, that is the length of line of the core. So we're neglecting, we're not saying this length or this length, we're taking the mean of this length. So in that case it will be equal to L into C. So H cross L into C, this actually multiplied, it is not across this vector multiply. H into LC is equal to Ni, so H can be calculated as Ni by LC. So as I told you earlier, its unit is ampere turn per meter, or I can write it in this form, HCLC, that is the magnetic field intensity in the core multiplied by LC, that is the mean length of the flux line, is will be equal to N into I. This is one of the most important relation that you need to first uh, make sure that you know this and you have studied this. You have to always remember this. Now coming to the next point, that is the magnetomotive force, that is usually this denoted by the F. It is also equal to N into I. So this magnetomotive force is nothing but, we can say it's just like electromotive force. You know that electromotive force in electric circuit will force the current to flow in the circuit. Similarly, this magnetomotive force in the magnetic circuit will force the flux to flow in the magnetic circuit. That is how we usually usually solve this magnetic circuit by the electrical analogy. So you will come to know soon what will be that electrical analogy. So one more thing that we need to understand, that relationship between flux phi and the flux density B. So this is flux density. So we know that phi is equal to this close integral of B dot ds. So for the same reason, if B and ds are in the same direction, this will be equal to B into ds, and if B is constant on the surface, you will see that B will be taken outside and ds can be replaced by A, then this phi will be equal to B into A. Now we'll try to find out the relation of the reluctance. As I have told you, reluctance is nothing but the property of the magnetic material, um, in which it opposes the passage of the flux lines. So this is quite similar to that of the resistance that opposes the flow of the current. So phi is equal to B dot ds, where B is equal to mu into h, it will be equal to mu dot ds. So mu is a constant to be taken outside, and as I have told you that h into ds, they might be in the same direction. I'll just try to make you understand. For example, it is a side view of the score. This is the side view of the score. When you look at the top view, it has some breadth, and due to that breadth, it will make area. I'll just show you that if that is over here. Yes, this is the side view of the core. This is the top view of the core. You can see uh, the flux lines comes up from this point like this. This is point A, and then goes like this line, and then it will go down from here like this. So flux line actually encounters this area. You will see that we always have an area vector. This area vector is perpendicular to this vector. Flux line comes up, and this area vector is also in the upward direction. So flux line and the area for this type of the system will always be in the same direction. So in that case, you will see that this B dot ds will nothing but B into A. So that's what I want to make you sure. So that's what I have. This flux is equal to B into A, where B is the magnetic flux density in the core. A is the area of the core. So now coming back to reluctance, this H dot ds is equal to H is constant in the core everywhere. So this ds will be equal to A. So I have just shown it. So phi is equal to mu H into A, or it will be simply B into A. So but H is equal to Ni by L. I have just shown it from the previous slides. It can be equal to Ni by L. See. So phi is equal to mu A mu A into Ni by L. So I will write it like this: Ni divided by L. I will divide mu A to the numerator as well as denominator. It will be equal to L divided by mu A. So phi is equal to F by R, where F, as I already told you, is equal to this Ni, which is the magnetomotive force, and R is equal to L divided by mu A, that is the reluctance of the circuit. It is analogous to the resistance because resistance is also directly proportional to length and inversely proportional to the area. So resistance will be equal to rho L by A. This is equal to 1 by mu L by A, because this mu and rho, they we can say like this: the rho that is doing for the resistance, here it is 1 by mu that is doing for the reluctance. It is not directly, we cannot use directly this mu in place of rho. We have to replace rho divided by rho by 1 divided by mu. So it is, we can say it is analogous to the circuit. So reluctance is the property of the magnetic circuit to oppose the passage of magnetic flux line, as I have told you earlier. So its inverse, that is reluctance 1 by reluctance, is known as permeance. Permeance will be the property of the magnetic material to support the passage of the magnetic flux line. Sometimes permeance may be used instead of this reluctance, as we have done in electric circuit. We are using the conductance in place of resistance, because conductance will be the inverse of the resistance. Now just to describe the analogy between magnetic circuit and electrical circuit. In electric circuit, V is equal to IR. We can say this is the Ohm's law for the electric circuit. And in magnetic circuit, this magnetomotive force will be equal to phi into R. This will be the Ohm's law for the magnetic circuit. So V is the driving force in electric circuit. Here, magnetic circuit, F is the driving force. So the result for, or we can say the effect will be in electric circuit will be the current, and here it will be the phi. So the opposing quantity in case of electric circuit is R, opposing quantity in the magnetic circuit is this reluctance, capital R. So if this is an electric circuit, where V is the forcing function, I will be flown through this and it will be decided by the value of this R. Similarly, we will be having a forcing function of F, that is the magnetomotive force. It will try to draw the flux phi depending on the value of this reluctance. It will try to oppose this. So this is actually a magnetic circuit. So this is the driving force N into I. I have replaced over here, and this is RBE. That is the reluctance between the point B and E. That will be shown by resistance is R. So this limb will be replaced by a resistance RAB. Actually, this is the reluctance. It's not a resistance. So magnetic circuit has been replaced by an electric circuit. This will be RAB. That is the reluctance between A and B. This AF. This is the reluctance between A and F. Similarly, F and E. This is represented by a resistance. That's reluctance between E and F. Similarly, for this case, this is BC, reluctance of BC. This will represent the reluctance of CD. This will represent the reluctance of DE. Sometimes, since all the reluctances are in series and they carry the same flux phi 2, they can be combined to have the same value. That is, we can have simply R equivalent, that will be equal to RBC plus RCD plus RDE. And here, this phi will be equal to phi 1 plus phi 2. So from this, I have this represented this circuit again. So this phi is equal to phi 1 plus phi 2. This phi is equal to phi 1 plus phi 2. It is a key cell in magnetic circuit. And Ni will be equal to RBE into phi, this phi, plus phi 1 into RAB plus RAF plus REF. Similarly, we can write it as it's equal to F is equal to Ni, that is equal to phi into RBE plus phi 2 into RBC plus RCD plus RDE. So in general form, we can write it as like this: summation from 1 to n phi I Ri, that is equal to Ni. That means total magnetic this magnetostatic drop, that will be equal to the forcing function. This is actually the voltage drop, analogous to the voltage drop in the electric circuit. Sometimes it may be replaced by this magnetic field intensities terms as well. That is, HILI will be equal to Ni. So this is the form of the KVL in terms of magnetic circuits, and summation I is equal to 1 to n, phi is equal to 0. This is the form of the KCL in magnetic circuits, because here you can see phi, I can write it like this: phi minus phi 1 minus phi 2 is equal to 0. That is what this equation means. So this is how we can write the KVL and KCL in terms of magnetic circuits. Now let us try to describe one more circuit in which we have an air gap. So when we replace it by an electric circuit, we have Ni, that is the forcing function. We have the reluctance of between A and F. We have the reluctance of between R and this A and B. We have the reluctance of between B and C. We have the reluctance between C and D, reluctance between D and E, and reluctance A and F. But in this case, you will see that the reluctance of all the core limbs will be same. Only thing will be they will be dependent upon the length. So I can write it as like this. This is Ni is equal to Rc plus Rcd, but the reluctance between this core and this air, it will definitely different, because they are two different materials. It will be different. So I will replace all these by this Rc, that it represents the reluctance of this whole core, and this Rcd, that is this, it will represent the reluctance of this air gap, that is Rg. So where Rc is the core reluctance, it will be equal to Rab plus Rbc plus Rde, that is this, plus Rfe plus Raf, and Rg is the air gap reluctance, that is Rcd. So it can be replaced like this. So from the equivalent circuit, Ni is equal to phi, because there will be total flux phi, that is this flowing through this. This Ni will be equal to phi into Rc plus Rg. Phi will be equal to this Ni is equal to phi into Rc plus Rg. And this Bg is the magnetic flux density in the air gap, and Bc is the magnetic flux density in the core. You will see that whenever the flux line comes over here, it will directly flow through this. We'll assume there will be no fringing. Actually, there will be fringing at this, and the flux lines will be off like this and off like this, and we'll assume there will be no fringing, or will neglect the fringing. So what are the flux line that passes from B to C, that will directly pass to C to D without having any fringing effect? So in that case, we can say there will be no bulging of the magnetic field. Magnetic field when flux density will be same here and here. So in that case, this phi will be equal to Bg into A. It will be equal to Bc into A. The flux that passes through here will be same over here, because area of the core will be same at this point. Area of the core in the air gap will be same, because there will be no flux that is flowing or that is bulging at this point like this. That's making curve. It is again flowing in the straight paths. So now reluctance is equal to, this is L, that's the length of the core in which flux will flow, divided by mu into A. So for RC it will be equal to LC divided by mu C, that is this permeability of the core multiplied by area. In this case area will be same, and it will be equal to LC mu naught mu R into A. Mu R will be the relative permeability of the core. So Rg will be equal to Lg divided by mu naught into A, because for practical purposes mu R for the air will always be taken to be equal to 1, and I will show you why it is taken to 1 in the short while ago. So for the time being we will take it as Lg divided by mu naught into A. So okay, so I have described this, but first let me come to this. So Ni is equal to phi into Rc plus Rg. So taking this Rc is equal to phi is equal to B into A, Rc is equal to Lc divided by mu naught mu R into A, that is this Lc into mu naught mu R into A, so plus Lg divided by mu naught into A. So this A and A will cancel out, this A and A will cancel out, taking B and mu naught outside. So Ni will be equal to B divided by mu naught Lc divided by mu R plus Lg. This is the important result, and from this equation you can find out any unknown if other knowns are given, if other parameters are given. For example, if you are given the value of B, LC, mu R, LG, you can find out the value of Ni or simply I. Or sometimes you may be asked to find out the B, and these quantities are given. So you can find out any parameter if other parameters are given. This is a very important equation. One more thing that I have told you, that this is the side view of the core and this is the top view of the core. You need to understand the core area as well. As I have told you, this is the core area in which flux will try to find this flow. You can see over here, this is the core area. It is we can see it is not the top view, it is the intermediate top view and the side view. This is the side of this, and this is the top of this. You can see top will look like this, and the magnetic field, magnetic flux density will be of this type. It will flow through this core, or this will be magnetic flux lines will be facing this area, this core area. So here it is very important to understand the LC, that is the length, or we can say path through which the magnetic flux line will flow, and also the area it encounters while flowing.